What's up, folks? This is Pierre-André Mathieu, and I'm here today with a tutorial on how to basically get the movement input with both controller and keyboard. Like this. I'm pressing the keyboards W, A, D, and S. Something's wrong with the A. I might have to fix it. Yeah. And I'm using a controller to move. So what I'm gonna show you in this tutorial is how to basically have the best of both worlds without using the enhanced input, that is. And I'll explain why in a matter of moments as I go along with this tutorial. Alright, this right here is what's called the Legacy Input Manager. I'm using this instead of enhanced input while Unreal Engine has officially deprecated this system. There's like a lot of practical reasons why I've chosen to stay with this for this specific type of project involving character action video games. Now, I'm going to explain why this system currently fits within my workflow. Legacy access mappings are always on and fire every time, which makes it incredibly easy to pipe that raw continuous flow directly onto my blueprint interfaces, in which I will explain on my next segment, without having to manage the complex trigger state logic started, ongoing, and triggered required by enhanced input. Enhanced input requires that I create multiple assets for every action, albeit input actions and input mapping context, which is too much of a hassle for me. In my current engine input settings, I have everything visible in one single menu: move forward, move right, lookup rate, and turn rate. For a solo developer, the legacy system allows for much faster iteration without the overhead of asset management. What I have here is basically showing that I'm using scale 1 for most inputs, but for input such as the S key or down arrow key, I use -1. The legacy system handles these investors globally at the project level. In enhanced input, I would have added modifiers to each individual key binding within a mapping context, which adds extra steps when I just want to get a character moving. And because I have a complex function that relies on smooth interpolation, the legacy system's constant execution provides a reliable heartbeat for my rotation logic. Because with this, I don't have to worry about the input falling asleep whenever the thumbstick is at a neutral position, which can sometimes happen with improperly configured enhanced input triggers. Even though this yellow warning in here says that these things are deprecated, they'll continue to work for the foreseeable future. I have no intention to implement complex features like input rebinding for players in the game's option menu. So yeah, in stuff like this, the legacy input system is my best option. Now let's move on to the blueprint interface, and what I have here is what's called the character, more specifically player character blueprint interface. And if you want to create a blueprint interface, just simply right click, go to blueprint and click blueprint interface. Then once you have your new blueprint, you can rename it to wherever you want, but for me, I just call it player character blueprint interface. What I created here is a highly modular and efficient input handling system with the use of blueprint interface. By creating this specific movement input function within my player character blueprint interface, I've made a universal bridge to pass movement commands from my controller to my character without hard coding them together. By using this blueprint interface instead of standard functions or events on the character itself, I'm avoiding casting. My player controller doesn't need to know what specific character class is possessing. It just sends a message to whatever actor it currently controls saying, hey, I have a movement input for you. If my game allows the player to possess different types of characters, the controller just fires the same blueprint interface message. Every specific character blueprint will implement this interface differently to handle the movement in a way that makes sense for them. Rather than creating two separate interface functions, I consolidated them to a single function using two specific inputs. This green float pin is the access value. It passes the raw analog data, usually from -1 to +1, coming from the thumbstick, telling the character how fast or how far to move. This dark green pin there, the left thumbstick access type, is basically a clever part of any design. In fact, it's by far the most sane part any designer can do. By passing a custom enumerator, I'm telling the receiving character which direction the access value applies, albeit x-axis versus y-axis, or forward back versus left right. So what I've created is a clean, scalable, and cache-free input system, keeping my event graph tidy by funneling all left thumbstick movement through a single node, as it uses a switch enumeration system on the receiving end to route the X and Y movement logic appropriately. It's a very standard professional approach to handling character possession input, especially when creating in action video games like Devil May Cry, Bayonetta, or Metal Gear Rising. The next part is the left thumbstick access enumeration, like the one I have here. If you want to create something like that, just right click, go to blueprint, and create enumeration. After you have a new enumeration like this, you can rename it to whatever you want, but I'm just calling this E left thumbstick access, just to make things a lot simple. Actually, keeping it simple is what I meant to say, but you get the point. Anyway, let's open this up. What I created, it is a specific asset to basically act as a traffic director for the blueprint interface in which I've created on my previous segment. This enumeration is the crucial missing puzzle piece within my input system. A thumbstick essentially splits out raw dumb numbers. It just says my value is 0.8. On its own, the character blueprint receiving that 0.8 has no idea what the hell to do with it. Should it move that character forward or sideways? I created this enumeration with left thumbstick y-axis and left thumbstick x-axis and passing it through the blueprint interface alongside the float value. I'm giving that raw number context. What I'm saying is I'm effectively telling the game, here is a value of 0.8 and it specifically belongs to the y-axis. In Unreal Engine, enumerations are extremely powerful when paired with switch nodes. Because I designed this enumeration, the receiving character blueprint can use a switch on E left thumbstick axis node. This creates a perfectly clean fork in my code. If I use y-axis, I route the float value into an add movement input node using the character's forward vector. If I use x-axis, I route the float value into an add movement input node using the character's right vector. Without this enumeration, I would have had to make my blueprint interface messy by either creating two separate functions, that being movement input Y and movement input X, or create two separate float pins on a single function, which means one pin would always be sending useless zeros data every time the other access fired. To put it bluntly, I made this enumeration to elegantly pack directional intent alongside my numerical input data. It keeps my interface functions consolidated and makes the logic on the receiving end as simple as flipping a switch. Alright, now let's move on to how I added this blueprint interface into my player character. The first thing I do is I go to class settings. Then within the class settings, I go to interfaces and at the bottom of inherited interfaces, I click on Add on Implemented Interfaces, then type into search for player character, in which I have right here. By implementing the player character blueprint interface, which I have here, within my player character blueprint, I've basically signed a contract that allows this specific character to understand and react to the movement messages in which I've explained earlier here within that segment that involves the character blueprint interface. In Unreal Engine, simply creating an interface isn't enough. An actor must implement it in order to gain its functionality. The blueprint interface in which I design acts as a radio frequency. By adding it to the implemented interfaces list in my player character blueprint, I'm tuning the character to that frequency. Now, when my player controller sends the movement input message, this character blueprint can actually hear it and trigger the corresponding event in its event graph. Once implemented, the functions I defined within the blueprint interface appear in my character's logic as events, like the one you're seeing right here. This allows me to right-click in the player character blueprint event graph and search for event movement input. And because I implemented it, I can now write the actual code using my enumeration and access values that tells the mesh how to move. In game development, and as my character gets more complex in, say, adding melee attacks and finite state machine logic, my code can become basically a spaghetti of references. In implementing the interface, my character doesn't need to know anything about the player controller. It just waits for the interface event to fire. This keeps my player character clean and prevents the engine from having to load a bunch of unnecessary stuff every time I open this blueprint. If I decide to add a different character, I can simply implement this same player character blueprint interface on that new blueprint, or simply put add a child blueprint of the player character like this. Even if their movement logic is totally different, the player controller can treat them exactly the same way by firing the same message without needing to know which character is currently active. Simply put, implementing this in the class settings allows me to turn my character from a static mesh into a listener that is ready to process the input data coming from my enumeration-based system. This logic I built here for the y-axis movement within the player character blueprint is made specifically to create a smooth, highly responsive feel by calculating a dynamic move speed before applying physical movement. Instead of applying the axis value directly to a movement mode, I'm first rotating the y-axis input into a make vector 2D node to update an input vector variable. And do keep in mind that variables like this are inherited from the character blueprint right here. Which means that any variables that the child blueprint has is inherited from the character blueprint. Anyway, by breaking and making the vector, I ensure that the y-axis is stored correctly while preserving whatever x-axis data might already be present. This creates a consolidated 2D representation of the thumbstick's physical position, which I then use for all subsequent speed and threshold calculations. What I implemented here is a sophisticated check system to determine the character's movement state. I'm taking the vector 2D length of my input and comparing it against a walk threshold and a run threshold. Through a series of AND gates and select nodes, I determine a target move speed, 1 for walking and 3 for running. This ensures the character doesn't just snap to full speed if the player is barely nudging the stick. One of the most important parts of my y-axis design is the float interpolate to logic. This prevents the character's speed from changing instantly. which would look robotic. I multiply delta I've multiplied delta seconds by custom time dilation before plugging it into the interpolation. This ensures that if my game enters slow motion, the character's acceleration and deceleration remain physically consistent with the slowed world. In case if you're wondering where delta seconds comes from, it comes from the character blueprint. I simply extract delta seconds from event tick, promote it to a variable, and leave it like this. Anyway, the final move speed slides smoothly toward the target move speed at a constant interp speed at 15. Finally, I take that process move speed and apply it to the add movement input node. I'm using the forward vector derived from the camera yaw. Which comes from the character blueprint. I use get camera player to transform component and get world rotation. Then break the rotator to make the rotator to basically have this camera work in accordance to the camera blueprint, in which I've already covered within the previous tutorial. What this means is that the forward on my y-axis always follows where the player is looking, which is standard for modern third-person action games. I use normalized 2D mode on my vector before applying speed, which is a critical design choice as it prevents the diagonal movement bug where moving both forward and sideways simultaneously would make the character move faster than intended. And this stems from the input vector, get input vector to be precise. My y-axis logic also doubles as a state breaker. If the character is on the ground and the input vector length exceeds the walk threshold, I trigger a branch that can stop animation montage, which I have right here. It's likely designed so that if my character is mid-attack or mid-action and I slam the thumbstick forward to move, the movement takes priority and cancels the current animation to keep the gameplay feeling snappy. This one here is the X-axis movement. This design here is significantly more complex than the Y-axis because it incorporates combat-ready strafing and a custom logging system. While the Y-axis focuses on forward momentum, the X-axis handles how the character maneuvers around the target. I use a make vector 2D node to update my input vector. By breaking the existing input vector and feeding its Y back into a new make node with the fresh X input, I ensure that moving side to side doesn't wipe out my forward-backward data. This keeps the 2D movement compensate intact. My add movement input node uses a variable world direction. As you can see here, I added a bit of a wall running mechanic, but I am not going to tell you about that because there are things here in which I am not going to tell you. Right now, I'm just going to explain to you how the X-axis movement is. The rest, as you see right here, it works like the Y-axis, but different. Unlike the Y-axis where I use the pitch for forward and back, I use the roll for left and right. This is where my design shines for a character action game. I implemented a lock-on system that overrides standard movement rotation. I use a NAND gate and a branch to dynamically toggle the character's rotation behavior. If I am locked on and on the ground, I disable the standard face where. What I meant to say is I turn off the standard face where you are running behavior. And there's the face target. With this function, I use find and look at rotation and to calculate the angle between my character and the locked target, which is the character blueprint itself. I use rotation interpolate with an interp speed of 10 to make the character's torso and feet swivel toward the enemy smoothly rather than snapping instantly. This allows for that circling opponent to feel typical of high octane character action games. Also, like the y-axis in my previous segment, I use normalize 2D. This makes sure that if a player holds the stick at a 45-degree angle, the character does not move at 141% speed. It keeps the movement speed consistent regardless of the direction. Simply put, I designed the x-axis to be modular. By separating the input from the world direction, I created a system where the same thumbstick movement can mean straight flight in a duel, in this segment, I'm going to explain how this relates to the legacy input, in which I shown you on my first segment. By completing the communication loop between the raw hardware signals and the logic I build inside my character. I'm using Eventic to drive the actual communication. then I use a sequence node to keep things organized. On then 0, the controller reaches out to the get player character. Then it fires the movement input message node. Now, if you notice these small blue envelope icons on the top of the right of those nodes, that indicates a blueprint interface message. And from the access values of these movement inputs, I promote these to a variable and name them left thumbstick x-axis and left thumbstick y-axis. This part is where I capture the raw signal. I use the input access move right and input access move forward nodes. Those are the legacy listeners in which I've discussed again from my first segment. Because I define these in my engine input settings, these nodes are constantly firing every frame, even if the value is 0. I'm immediately saving these values into two variables, left thumbstick x-axis and left thumbstick y-axis. This effectively buffers the input so it can be used elsewhere in the blueprint. This is where my specific design choices from the previous steps all come together. I take my local left thumbstick axis variable and send it to the character. Crucially, I've manually set the left thumbstick axis type drop down to left thumbstick axis. This does the exact same for the y-axis. Manually set to left thumbstick y-axis enumeration value. Okay, I'm not going to toot my own horn or anything of that sort, but what I did is develop a controller to character, which is a very smart setup on my part, because the controller does not care which character is talking to, as long as the character has the player character blueprint implemented. This logic will work. By setting these variables on tick in the controller, I ensure that the character always had the most up-to-date intent from the player, which is vital for the smooth float interpolate and rotation interpolate logic I've built for movement and combat tracking. My input logic stays in the controller and my physical movement logic stays in the character. In other words, the controller is the voice shouting instructions every frame. The blueprint is the radio frequency, and the character is the listener that interprets those instructions based on the enumeration type I've assigned. If you think that's everything I need now that I've set everything up, well, this is the part where I say you might want to think again, because that does not stop here. What I have here is the Blueprint third-person game mode, and as I open it, it has all the classes here. Setting these values in my Blueprint third-person game mode is the last step that makes my entire movement system actually function when I press play. The game mode acts as the rulebook for my level, telling the engine exactly which actors and logic controllers to spawn. By setting player controller class to player controller blueprint, I ensure that the specific input logic I built is actually present within the game. If this were left as default player controller, then the engine wouldn't even know how to look for my thumbstick access variables or fire my movement input messages on tick. Setting the default pawn class to player character blueprint tells the game mode to automatically spawn my player character and place the player inside it at a player start. This establishes the connection for the get player character node I use in my controller. Without this setting, that node might return to none and my BPI messages would have no recipient, or in this case, default pawn. The game mode is what links the input settings to the controller and finally to the character. Because I've customized both the controller and the pawn, assigning them here ensures they possess each other correctly the moment the map loads. In short, I set this up here so that Unreal Engine knows to use my custom built logic instead of the generic engine defaults. Okay, now that I set everything up, let's put it to the test, shall we? Yep. I'm using keyboards. D is to move right, A is to move left, S is to move backward, and W is to move forward. If I'm tired of using keyboard, I can just use a controller. So yeah, I basically have the best of both worlds here. And that concludes for this tutorial. If you enjoyed this video, please like and subscribe to my channel for future tutorials regarding character action games. And do keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out, and I will see you guys on the next video.